Thank you for the introduction and good afternoon, everyone. I'm Ondřej Sladký, and this is the work we did with Pavel Veselý and Karol Břinda on FMSI, a space-efficient index for k-mer sets. K-mer sets are the sets of all substrings of fixed length from genomic data, as illustrated here with the case of k equal to 3. And they're used widely across computational biology, as an example in metagenomic tools such as Kraken, in search engines for large-scale genomic data, or in rapid diagnostics of infectious diseases. And when we want to build data structures that work generally for k-mer set, we need to understand the characteristics of the set that are used in practice. The values of k ranges from 3 to several hundreds, with the most common value being 31, and the sizes vary even more, from a few to more than hundreds of billions k-mers. And the structures of the k-mer sets depend heavily on several things, such as which sequencing technologies had been used, whether it's raw reads or assemblies, which species does it come from, and is it a single species or a pangenome, and whether sketching or subsampling has been used. And in all these applications, so-called colored k-mer sets are used, where k-mers are associated with additional data. However, the data structure for these inside rely on indexing single k-mer sets. Which brings us to the problem of how to perform queries on single k-mer sets, and we require two different functionalities. First, we want membership queries, where for a given k-mer, we tell whether it's present or absent in the k-mer set, and this is widely supported across existing indexes. And second, we want dictionary queries, where for every k-mer, we return a unique hash between 0 and the set size -1, while rejecting the absent k-mers, and this is currently supported only in SSH. And our goal will be to minimize the space of this index while still having a competitive query time. And if this is to work as a building block for other tools, we need it not to work only for specific model cases, but we want it to work well across different values of k, across different sizes of the sets, and for variety of structures of the k-mer sets. Currently, the state-of-the-art indexes rely on so-called De Bruijn graphs, where k-mers are vertices and an edge is between two vertices if the k-mers share an overlap of k-1. So for instance, the Masked Burrows-Wheeler Transform represents these by storing for each k-mer its successors in this graph, and other tools such as dbGFM or SSH store these De Bruijn graphs in the form of simpletics, which are compacted paths in De Bruijn graphs. And these methods have good compressive properties for model use cases, such as the human genome with k equal to 31. However, when we use them with pangenomes, with small k, or we use subsampling or sketching, they become highly inefficient. So in our previous work, we proposed a compact representation via masked superstrings, where we represent the k-mer set with its shortest superstring and an additional mask, which encodes which k-mers in the superstring are actually from our set. So for instance, for the following set, we get this superstring, which contains all the k-mers as substring, and then we complement it with a mask, where 1 tells us that the k-mer is from the set, and 0 tells us that it is not. And since it is sufficient to mark a k-mer present at least once, there are many masks possible. However, computing optimal mass superstrings is NP hard, and both for the superstring and for certain mask optimizations. Therefore, we have to rely on approximation algorithms to compute the superstrings, and a classical one that is widely studied in the literature, which proceeds by merging two k-mers by their largest overlap, computes a short-range superstring in linear time. However, there are no practically efficient general implementations, and therefore we implemented this algorithm efficiently for the case of k-mers in k-mer-KMO with a important optimization that the first step of this algorithm is actually equivalent to computing simplicities, for which efficient solutions already exist. And the superstrings computed with this algorithm are close to optimal for k-mer sets, and both for the more traditional sets and some where for instance, subsampling is used, and it outperforms its counterparts based on de Bruijn graph representations. But this brings us to the question, how do we index mass superstrings? And the first obvious issue is we somehow have to deal with the mask, which makes full text indexing not sufficient, as we would either have false positives, or we would have to, for every occurrence, retrieve the original positions, which would be too costly. But there are other issues which are not specific to superstring indexing, such as how do we handle reverse complements if we do not want to double the size of the index, and this is especially important and not previously done when we want to have fast streaming queries. Nevertheless, it brings us to the problem, how do we jointly index the superstring and the mask? And for this, we propose Masked Burrows-Wheeler Transform, which complements the standard Burrows-Wheeler transform with the so-called SA transform mask. And how do we get this? Starting from a mass superstring, we first compute the matrix of sorted rotations of the superstring, the so-called Burrows-Wheeler matrix, and we glue the corresponding mass symbols to the superstring counterparts. And as usually, the Burrows-Wheeler transform is the last column of this matrix, and the SA transformed mask will be the first column of the mask in this matrix. And this will enable us to query the k-mers that are in the superstring while not having false positives. So we want a data structure that supports membership and dictionary queries, and we can do this starting from an input k-mer set. So we first compute an approximated shortest superstring, then we optimize the mask, which is specific to whether we want to do membership or dictionary queries. Then we compute the masked Burrows-Wheeler transform, and additionally, we build auxiliary rank and select data structures on these vectors. And this can be done in linear time, and more importantly, we give strong theoretical guarantees for an arbitrary k-mer set of 2 bits per superstring character plus the entropy of the mask. So how do we do dictionary and membership queries in FMSI? We first retrieve the suffix array interval of the k-mer's occurrences, which can be done by a standard backward search. And if this interval is non-empty, we then verify that the k-mer is actually present using the SA transformed mask. And if it is present, then for membership queries, we return that it is present. And for dictionary queries, we return the hash from 0 to the size -1 by asking the rank on the SA transformed mask. And The last two steps can be done in constant time. So the time complexity is dominated by the standard backward search. So it's linear with the size of k. But we can do better if the k-mers come from a stream of k-mers where consecutive queried k-mers overlap by k-1. And there we can do constant query by using the KLCP array and saturating counters even when we consider the reverse complement. However, this is a bit technical, so I won't go much into details. And we implemented this in the FMSI program, which is available at GitHub. So now to the experimental evaluation. And since the existing tools are mostly optimized for model use cases, such as the human genome with k equal to 31, we performed an extensive evaluation where we considered various data sets, which include both reads and assemblies. And we evaluated it across multiple values of k and compared ourselves to 3 other tools, the CBL, which is a recent dynamic index, SSHash, and the Masked Burrows-Wheeler Transform in 2 variants, SBWT fast, which is the default one, and SBWT small, which is a one with hyperparameters tuned to be space efficient. And on all of these data sets, FMSI outperforms its counterparts. And we'll now focus on one of these data sets, the high quality E. coli genomes from the 661K database. And here, FMSI requires no more than 3.5 bits per canonical k-mer, while even the space-efficient SBWT requires up to 2 times more. And for instance, SSHash requires 2 to 6 times more, and CBL 10 to 50 times more. And to verify that our tool is not only space efficient, but it still retains competitive query time, we consider still this case with the E. coli pangenome, and here we can see that while it's about 3 times slower than SSH and the fast SBWT, it's still twice faster than the small one, so it's roughly in the mid-range of these methods. However, since FMSI provides general compressive properties for other data sets where previously the methods fail, such as when we use subsampling of the k-mers, we performed an experiment with Kraken indexing on the mini Kraken database where the k-mers are subsampled. And here, this depicts the memory for the dictionary queries with the additional 2 bytes per k-mer for SSH and FMSI to store pointers to the taxonomy tree. And here, FMSI outperforms both the original Kraken and also SSH by more than 2-fold times. So to conclude, we built an index that combines the idea of representing k-mer sets with masked superstrings and using the Masked Burrows-Wheeler Transform. And it is the only index which has strong theoretical guarantees for arbitrary k-mer sets. And this is consistent with the experimental evaluation, where it is the most space efficient index across data sets, different values of k, and even with sampling. However, there are still a few limitations of this. First, and mostly the implementation ones, which is the speed of the Burrows-Wheeler construction, and also the fact that the queries are currently not parallelized. And it opens some additional future work. One of them is how do we make this index dynamic? That is, for instance, to at least support set operations on it. And we focus on this in our follow-up paper. And another important thing that would be done is to extend this data structure to work with colored k-mer sets. And this is all from me. I would like to thank Pavel and Karel for the wonderful collaboration, and to you for your attention. And I will be happy to answer your questions.
We do have time for questions, so please, I think we have a question at microphone 2.
Thank you for a nice talk. Just a technical question, because maybe I missed one point. When you use this masked Burrows-Wheeler, when you sort cyclic shifts or suffixes, do you sort them already with masked bit or without it?
Yeah, thank you for the question, and it's a good one. We sorted without the mask bits, because otherwise it would spread the occurrences of k-mers elsewhere. So what is done is that the Burrows-Wheeler is computed for the superstring, but additionally we kind of shift the mask bits in the same way as we do with the superstring bits. So I might go to the slide where this is. So this matrix is just of the superstring characters, and always the mask symbol corresponds to what was the mask symbol at that position of that particular symbol.
Yes, that's clear. So then when you do the search, the backward search, you are just finally you get a range, and you just ask a query whether you have at least one in this range.
Yes, and we can actually do a bit better if we use mask superstrings which maximize the number of ones, because then we can only actually look at one position in that mask afterwards. But yes, that's basically what is done.
Okay, thank you.
Thank you for the question.
So a question at microphone 1.
Yeah, thank you. Really great talk, really interesting work. So my question is kind of maybe related to your future work slide, but when you have, these really large k-mer sets, when you're using them in different applications, oftentimes the satellite data become the storage bottleneck, right? So like the color set with the colored k-mers, or positional information if you want to actually go back to the place in the reference genome where this k-mer occurs. My question is, you have this degree of freedom in how you choose the masking string. Do you think that there's an optimization problem here, where for different types of satellite data you might want to optimize the masked strings in different ways? And do you have any sense of like what kind of difference in performance or size that might lead to?
Thank you for the question. So my answer to this would be that this basically comes at the relevance, I would say, of the dictionary queries, because if you have additional data for the k-mer, the best way I would say is to store it. Basically, if you have a unique hash from 0 to the size -1, you can then store it in an array which is outside of your data structure. And so then you basically don't lose any space because it's not spread out. So, and for that you need the masks to actually minimize the number of ones, because otherwise you wouldn't get this property. And it does worsen a bit the compressive properties of the mask, but not by large extent. It's very small, tiny, I would say. I don't know if this answers your question.
Yes, but I think I'd like to chat more. It's thank you very much.
Thank you.
Okay, so I think we don't have any more questions, so let's thank the speaker again.